In our class, we will discuss two different types of motion graphs for the most part, position versus time and velocity versus time. With position versus time graphs, these are the main things that we need to be able to do. Everything relates mainly to slope and how that relates to the object's motion. So we'll take a look at each of these points individually. First, it's important to understand what the axes are telling us. This graph would be titled Position versus Time because position is on the vertical axis or the y-axis, and because time is on the horizontal axis or the x-axis. So the name of the graph always corresponds to the vertical versus the horizontal, or the y versus the x. When we make our graphs of motion, we almost always put time along the horizontal axis, no matter how the information was gathered. So position will be on the vertical and time will be on the horizontal in the graphs we look at today. So what do those axes tell us about the slope? Well, we can really take a look at just our basic definition of slope, remembering that it's the rise over the run. And if we match that up with how our axes have been labeled, just looking at what's on the vertical axis, what's on the horizontal axis, we can see that for this graph, our slope will tell us something about meters over seconds. The slope will have units of meters per second. So it's a velocity. Without really memorizing anything, just looking at the graph, we can tell what the slope is going to tell us. So how does that relate to the object's motion? Well, we're going to need to break this graph into three parts because there's three very distinct slopes in our graph. Again, keep in mind that slope is telling us about the velocity, how fast and in what direction. So let's look at this yellow section first. This is a positive slope. We can see that the object goes from position 50 to position 100, so it's moving away from the origin, and this lasts about 20 seconds. If we look at the next section, here the graph is flat, the slope is 0. This object is not moving. It has a velocity of 0. It just stands still at that 100-meter mark for those full 10 seconds, 20 to 30. And then in our last section, looking from t equals 30 to 40 seconds, here our graph now slopes downward. A negative slope means the object moves toward the origin, back towards the direction it originally came from. Our slope value, it would be negative, but it would also be a much greater number than in the yellow section. So we know that it's traveling faster during this red section. So how do we actually calculate those values of slope? Well, remember that, of course, slope is rise over run. So we need to choose 2 points on the line. You have to do this in sections because the slope keeps on changing at various sections of the motion, various parts of the motion. So let's look at that first section that was highlighted in yellow a minute ago. And we'll look at these 2 points, easy to read from our graph. And we'll see that the object moves 50 meters in the positive direction from 50 to 100, and that takes 20 seconds. So our rise over our run, 50 meters over 20 seconds, equals 2.5 meters per second. Notice it's really important that you get your slope in the right order. If you're the kind of person who accidentally switches the run and the rise, your graph will be telling you seconds per meter instead of meters per second. So use the units to help you get those in the right direction, right, the right order. All right, let's look at the last section here. Okay, so here we go from 100 meters all the way down to 0 meters. I'm just looking at the vertical part of the axis, the meters part. So we go backwards 100 meters, so that would be negative 100, and this takes 10 seconds. And so our slope would be negative 100 over 10, or negative 10 meters per second. Now I didn't actually calculate that little section between 20 and 30 seconds because I can see without any calculation that the slope there is 0. The velocity is 0. Now, incidentally, the speed in the red section would be 2.5 meters per second, but the speed in the green section would be just 10. So we state speeds as always positive values. Velocity, we do something to indicate which direction the object moves. All right, so let's look at displacement and distance. We'll start with displacement, and again, we'll look at each of those 3 sections that we examined just a minute ago. Let's remember that displacement is how far between 2 positions the object has sort of traveled, what's the distance between those 2 positions, and it really doesn't matter what path they took. It's just comparing those 2 positions without really thinking about how the object got from one point to the other. So if we look at this first section, we can look at those exact 2 same points we did for the slope, but notice we don't care about time. This question is just about how far the object went. So it went in the positive direction, and it went 50 meters, from 50 to 100. So the displacement would be positive 50. In the next section, the displacement is 0. The object is standing still. And it goes from 100 and it stays at 100. And then the last section starts at 100 meters, ends up at the 0 position. So it's traveled 100 meters, but toward the origin in the negative direction. So that would be a displacement of negative 100 meters. All right, well, what if our question was a little more complex? Here the object is traveling between, we're just looking at the positions where it was at 10 seconds and where it was at 35 seconds. So let's see where that is on our graph. It's helpful to sort of highlight those on your graph itself. And again, all we're concerned with is the vertical axis of our graph. The horizontal tells us about time. Displacement is just about where the object is. So it went toward the origin 25 meters from 75 to 50, and so that's a negative 25. Sometimes people do better with these questions if they sort of write out something more formal. So if we wanted to really get a little more mathematical, we could say that it started at 75 meters, so we could call that x sub 1, and it ended at 50 meters. And when we calculate a displacement, delta x, we take the later position minus the earlier position, and that makes sure that our sign is correct. So we would get that negative 25 meters with this calculation. Now, what if the problem asked instead about the distance the object travels? All right, well, let's remember what distance is. Distance has to do with how far the object travels between 2 positions, but the path matters. The value of distance, though, is always going to be positive. It's kind of like counting footsteps almost from one position to the other. So in this case, we have to pay attention to the fact that the object moved from 75 to 100, and then it came backwards to 50. So the object actually had to travel 25 and then 50 for a total of 75 meters. Again, state that as a positive number. We have to pay attention to direction as we look at the graph, but the values, we only really care about the positive value, absolute value. All right, so what happens if our graph happens to be curved? We've only looked at really sort of straight lines. Let's take a look at the C graph in this one. This is a graph we'll look at in a later video. But let's look at the C graph and notice that in the beginning, the slope is very low, okay, very shallow. A little bit later, The slope is getting greater, the line is getting steeper. At the end, it's very steep. So what this means is that the slope is increasing, so the velocity is increasing. So we would say that this object is accelerating. It's a very smooth acceleration because the graph is curved. And again, this is a topic that we'll get to a little bit later.